In this tutorial, we'll be making a big leap towards automating Where's Wally. We'll modify the function that we wrote in the last tutorial to do object detection. In this tutorial, we'll detect a small template within a simplified image. And once we perform object detection, we'll circle the detected object like we have previously. To do this, instead of just performing convolutions, we'll employ similarity measures to do template matching instead. A similarity measure S takes in a template and an image patch and returns a result indicating how similar the image is to the template at that location. The one that we'll be using in this tutorial is called Zero Offset Normalized Cross Correlation. It is invariant to shifting and scaling the image intensity, so this will ensure that when we're finding Wally, that we don't accidentally miss out on finding him because the template we have of Wally is slightly duller or brighter than the image of Wally in the crowd. To calculate the zero offset normalized cross correlation, we'll separate the calculation of the numerator and denominator. The numerator is a convolution between image 1 minus the average intensity and image 2 minus its average intensity. The denominator is calculated by first subtracting the average intensity from each image, squaring each element, summing all the elements in each matrix, multiplying them together, and then finally taking the square root. Since the denominator calculation is a little bit complex involving lots of operations, it's going to be pretty easy to get wrong. One way you can make sure you're right is by checking when the two inputs to the function are the same, the result is 1. And the same is true when comparing the input with any shifted and scaled version of itself, because this similarity measure is invariant to shifting and scaling one of the inputs. So in this tutorial, we'll write a function that calculates a similarity measure between an input image and a template. To do this, we'll reuse a function that we wrote in tutorial 5, and we'll write a function that calculates the zero normalized cross-correlation similarity measure. And then we'll look at the results to see if we're able to successfully identify the object. We'll also reuse our circle function to plot a circle around the object. So let's move over to Matlab and get started. Okay, in this tutorial we've got a couple of tasks to do. We're going to write a brand new function, zero offset normalized cross correlation metric. And we're going to upgrade our image filter function. And we're going to be reusing our create circle function, which we wrote in another tutorial. And we're going to do object detection. Now, the way this code here works is tutorial 6 is the script, and then that'll call image filter. And then within image filter, we're going to use our zero offset normalized cross correlation function. So we'll start by writing the innermost one first and work our way out. So if we start here with this ZNCC function, we just need to calculate that one equation. So given I1 and I2, so two image patches that are the same size, we just want to calculate the ZNCC metric. First thing we'll do is we want to store the average intensity of image 1, which is just the mean of I1. And we just need to tell it that we want to do this over all dimensions of the matrix. So we just go help mean. Remember, by default, mean will work across the rows, I believe, or the columns. And we can do the same thing here for image 2. Okay, now let's calculate the numerator first. Now the numerator is simply the convolution between I1 and I2, and they're the same size, so all we do is go I1 minus I1 bar, and then that's dot multiplied by I2 minus I2 bar, and then we just want to sum these all together. So we go sum we want to sum over all the dimensions. Now we can just check that this function's working as we'd expect at the moment. ZNCC. Now first let's give it a, let's create I1 equals rand. Let's just do a 5 by 5 matrix, and then I2 equals rand 5 by 5 as well. And if we call ZNCC with I1, I2, good, we get a single number, so that's a good start. And now the denominator. We can take the first step from up here. First of all, I'm just going to work from the innermost brackets out. So we take this and then we square each element, and then we sum them all up. So sum all, okay. So we sum all those up, and then we multiply it. We do the same thing to image 2. So image 1 minus the average intensity, all squared, and then sum those all together. And then the same thing for image 2, but then we multiply these results together. And then we take the square root of everything, which is just using the Matlab function sqrt. Another thing you can do to just make this a little bit more robust is add the word real here. So if we take the square root of a negative, say -1, then we get I, because that's the square root of -1. But if we take the real square root of -1, Matlab throws an error. So we should never get a negative number here. So if we use real square root and we get an error, then we know we must have done something wrong here. Now, how can we check that this is correct? We can use our sanity checks that we talked about in the PowerPoint slides. If we use ZNCC on the same, and if we're comparing two identical images, the result should be exactly 1, and it is. Okay, we can also multiply this by some scaling factor, and we should also get 1. Good. We can also add an offset to this, and we still get 1. So it seems to be working. And we can, if we do it for 2 very different matrices, we get not 1. So this might be correct. And we'll see if it does the right thing later. Okay, so we've completed ZNCC so far. Now we just want to open up our image filter function. Now I've just gone and put in here all of our working code from the last tutorial. The only difference here is we've now got a second set of functionality. So if we still want image filter to just perform a convolution, if we just provide it with an image and a kernel like we did in the last tutorial, but then if we provided also a metric, we'd like it to use that metric instead of just doing a convolution. So this is now going to be a function that has a variable number of arguments. So there's only one small thing we need to do here to make this work for its old functionality and its new functionality. So metric here is a function handle. So it's just, you call metric the same as you call a function. So we're going to use Matlab's function called nargin, which tells you the number of inputs that a function was called with. So if we put a breakpoint here and we call image filter with, say, I1 and I2, it doesn't really matter. And then, now if we look at narg in, we get 2, because we call this function with 2 inputs, f and t. But if we call it with 3 inputs, now we get 3. So this is how we're going to determine whether we want image filter to do what it did before, just perform a convolution, or if we'd like it to perform its new function, template matching. So basically, if narg in equals 2, we're going to replace metric with convolution, and then here, instead of calling this, we will call gij equals metric patch t. And then, so now if this is called with 3 inputs, where the third input is the similarity measure that we'd like it to use, in this case ZNCC, it'll call that. But if it's called with 2 inputs, it'll still call metric, but that won't exist because there'll only be 2 inputs. So if the number of arguments is 2, we're going to replace metric with a new function, and we're going to do that using an anonymous function handle. So you can actually just go help for Matlab to tell you what that is. So we're creating a function handle. And we need 2 local variables here. We'll just call them A and B. And this is just going to perform a convolution as we did before. So it's just going to take this, but instead of patch and T, we'll use A and B. Now that should be everything we need for this function to perform both its old functionality and its new functionality. So just to recap, if we call this with 2 arguments, metric won't exist until down here where we detect that there was only 2 arguments, and then we define metric. But if we do call this function with a 3rd argument, metric, then we will not replace it with just this standard convolution. So if we call image filter with a metric, it will use that metric down here without replacing it. Now there's only a couple more things to do. So this is all just setting up and creating data and plotting, which we've all seen before. So what we want to do now is we want to call image filter, but instead of just doing a convolution, we'd like it to do template matching. So we need to give it, first of all, our input image, which in this case is called image, and the template, which is called template, which is just defined up here. Image and template. And then we want to give it our metric, which in this case is our function ZNCC. But the way we tell Matlab that this is a function handle is we put that little @ in front of it. So now we're actually passing the function image filter a handle to this function, so it can call it. Now, we want to find the pixel in G that has the highest score, because that should be the corresponding pixel in image, which is the center of our template. So to do this, we'll just use the function max, which we've used before. Just go help max. So So we want to find the maximum value in G. We don't want to compare it with anything, so we'll put an empty input. And then we want it to do all dimensions, not just over the columns or the rows. And because we're doing this, we need to tell it that we want it to use linear indexing. Okay, so if we run this now, we get M is 1. Now that means the maximum value in G was 1. Now we only ever get 1 when using ZNCC if we get a perfect match. And that was what we engineered in this scenario. We engineered this so that we would get a perfect match, which we won't expect in future when we're working with Where's Wally and things like that. So now we just need to convert index to sub-indexing as we've done before. So help ind to sub. We'll remind ourselves how that works. So vu equals ind to sub. Now we need to give it the size of the matrix, which in this case is G, and then the index, which is IDX. Okay, now U and V should be where our template appears in our input image. So 4 pixels across and 7 pixels down. Oh, now one thing we should do here, just go up to where this is plotted. We should turn on the axis so that we can actually count the pixels. There we go. So we're 5 pixels down and 9, so 9 pixels across and 5 pixels. Yeah, there we go, that worked. Okay, so now we just want to use, I'll just put this back up here. So now we want to use create circle to put a circle around the object once we've found it, just to indicate where it was in the image. Now if we want to remind ourselves how create circle works, just go help create circle. So we call it like this. So create circle, so we give it the center. So the center is U, V, and then we want to give it a radius. Let's just give it a 2 pixel radius. And we'll give it, and we get out of this X and Y, X and Y. And now we want to use plot, but we're going to do something a little bit different. We've only ever just used plot like this. We've said plot X and Y. But there's another trick using plot. You can tell it exactly what axis you'd like it to plot on. So if we just call it like this, it'll just plot over whichever axis was available at the time. What we'd like to do instead is we'd like to tell it exactly what axis to plot on. So here, this is the name of the figure, but here this is the name of the axis. It's called input underscore ax. Now if we do this, what it should do now is plot on exactly what axis we told it to. So we've not only found the object, but we've put a circle around it as well. There's only one more thing to do in this tutorial, which is use this function, which I don't believe we've used before, called contour F. So this plots a contour plot that's filled in, which is what the F stands for. So to use contour F, we just call contour F, and we give it the data we want to plot, which in this case is G. We can actually tell it how many level sets we want it to plot. We'll just use 20. With too few level sets, it can look cartoonish. Okay, and we can also make it not plot those ugly edges. We can go edge, color, none. Okay, so now we've got our ball down here, and where the ball appears in the input image should be the highest value in the similarity measure, which it is. And we know that's exactly 1 because it was an exact match. In this tutorial, we found a single object that perfectly matched our template. In the next tutorial, we'll be finding multiple objects in noisy images. And then after that, we're ready to find Wally.